Good day, everyone. We are Group 5, and today we will be reporting about the decibel scale. In this report, we'll explain what the decibel scale is, how it works, and why it is important in measuring sound intensity. Next slide, please. For our learning objectives, at the end of the lesson, the students will be able to first understand the concept of the decibel scale and why it is used to measure sound intensity. Second, be able to calculate sound intensity level in decibels, even sound intensity and vice versa. And lastly, to recognize the relationship between sound pressure, sound intensity, and human hearing sensitivity across different frequencies. Next slide, please. Now let's define what is the decibel scale. The decibel or dB is a logarithmic unit used to measure sound intensity or power ratios. So why is it logarithmic? Because our ears can hear a very wide range of sounds from the faintest whisper to the loudest rocket launch. So the decibel scale compresses this large range of sound intensities into a smaller and more manageable scale. This way, we can easily compare different sounds and understand their effects. So here we can see the decibel scale chart. At the lowest end, we have breathing at 0 dB. This is the threshold of hearing, the quietest sound a human ear can detect. A whisper is around 30 dB, while normal conversation is about 60 dB. And everyday sounds like a vacuum cleaner at 70 dB or truck traffic at 80 dB are already getting louder. And above 85 dB, such as air dryers or helicopters, sound can already start to damage our ears with long exposure. At the extreme end, you have jet engines at 130 dB and rocket launches at 140 dB. These levels can cause immediate pain and hearing damage. So this shows us how the decibel scale helps us understand the sound intensity in relation to our hearing safety.
Good day, everyone. Now let's go to why use decibels. The human ear can detect an incredibly wide range of sounds. The faintest sound we can hear is around 10 to the power of negative 12 watts per square meter squared, which is the scientific way of measuring intensity. To give you an idea, that's like the sound of a mosquito from a few meters away. On the other hand, very loud sounds like a rock concert or a engine can exceed 1 watt per square meter. Now, if we use these raw numbers, the range the range is just too huge to deal with. That's why we use the decibel scale. It compresses this large range into smaller, more practical numbers while still showing how loudness changes for our ears. Next slide, please. Next, how is the sound intensity level calculated? To make this simpler, we use the formula for sound intensity level in decibels. So that's the formula now. So here, the slanted I is the actual sound intensity, or it represents sound intensity, and the slanted I with O, or I sub O, is equals to 10 to the power of negative 12 watts per square meter, is the reference, or the quietest sound a normal human ear can hear. So this formula makes it possible to turn huge ranges of numbers into smaller, meaningful values. So the examples of problem solving will be using this formula will be discussed by Miss Toyor.
So now let's move on to the sample problems. So the problem is a jet engine produces a sound intensity of 1 times 10 to the power of negative 2 watts per square meter. Calculate its sound intensity level in decibels. So the formula we use is sound intensity level equals 10 log base 10 of I over I naught. So I is the given intensity, which is 1 times 10 to the power of negative 2 watts per square meter. I naught is the reference intensity, always equals to 1 times 10 to the power of negative 12 watts per square meter. So now let's substitute the values. I over I naught equals 1 times 10 to the power of negative 2 divided by 1 times 10 to the power of negative 12. When dividing powers of 10, we subtract the exponents. Negative 2 minus negative 12 equals 10. So we get I over I naught equals 10 to the power of 10. So let's now apply the logarithm. Log base 10 of 10 to the power of 10 equals 10. So let's multiply it by 10. Sound intensity level equals 10 times 10, which is 100 decibels. So the sound intensity level of the jet engine is 100 decibels. So our final answer is 100 decibels. That means the jet engine is extremely loud. 100 decibel is already a level that can damage hearing with long exposure. Problem number 2. A rock band produces a sound intensity level of 110 decibels. Find the corresponding sound intensity in watts per meter squared. So this time, we are not looking for the level, but for the intensity in itself in watts per square meter. So we start with the formula. Sound intensity level equals 10 log base 10 of I over I naught. So let's divide both sides by 10. 110 divided by 10 equals log base 10 of I over 10 to the power of negative 12. So we get 11 equals log base 10 of I over 10 to the power of negative 12. So let's convert from logarithmic form. So I over 10 to the power of negative 12 equals 10 to the power of 11. So let's solve for the I so we can get the value of I. Now let's multiply both sides by 10 to the power of negative 12. So I equals 10 to the power of negative 12 times 10 to the power of 11. When multiplying powers of 10, we add the exponents. So negative 12 plus 11 equals negative 1. So our final answer would be intensity is equal to 0.1 watts per meter squared. So you can explain at the end that the 0.1 watts square meter is very intense. It matches how loud a rock concert feels, which is why people usually wear air protection. So that's all for the problem solving.
Let's now proceed to the relationship between sound pressure and intensity. Sound has both pressure and intensity. Sound pressure is the force of sound waves acting on a surface, while intensity is the amount of energy carried by those waves. So the key relationship is that sound intensity is proportional to the square of sound pressure. This means that if the pressure doubles, the intensity becomes 4 times stronger. We usually measure sound pressure using the sound pressure level or the SPL, expressed in decibels. The formula is SPL equals to 20 log base 10, open and close parentheses of P over P ref, where P is the root mean square or the RMS sound pressure, and P is
And Pref is the reference pressure, which is set at 20 micropascals, the quietest sound that the human ear can hear. Next sound, please. Let's now proceed to the perception and weighting filters. Our ears do not hear all frequencies equally. We are most sensitive to sounds between 2 kHz and 5 kHz, which is the range of human speech. Because of this, sound levels meters use weighting filters to mimic how our ears respond to sound. A weighting and C weighting C weighting filters adjust measurements to reflect human hearing sensitivity at different sound levels. A weighting or the dBA, this filter reduces the low and very high frequencies, so it matches human hearing at moderate sound levels. It commonly used for noise measurements in workplaces and communities. And for C weighting or the DBC, these filters includes more low frequencies and is used for measuring very loud sounds like concerts or explosions. So in short, weighting filters help us measure sound the way people actually perceive it, not just the raw physical values. Next slide, please.
Finally, to conclude this presentation, let's remember the key ideas of the decibel scale. A tenfold increase in intensity adds to 10 decibels. For example, going from 10 to the power of negative 6 watts per meter squared to 10 to the negative to the power of negative 5 watts per meter squared adds 10 decibels. Meanwhile, if we just double the intensity, we add about 3 decibels. This shows how the decibel scale is logarithmic, not linear. What's great about this is that it actually matches how our ears perceive sound. Each jump in decibels feels like a noticeable increase, but not an overwhelming one, even if the physical intensity is multiplying. That's why the decibel scale is the most effective way to measure loudness. And that would be all for our discussion. Thank you for listening.